Chemical equation notes the entire thing down here at the bottom, the C3H8 plus O2 arrow CO2 plus H2O. That's the chemical equation. The parts of the chemical equation starting in the middle with the arrow, that is the yield part of the equation. Anything to the left, in this instance C3H8 plus the O2, that bracketed part, that part, the left side, is called the reactants. The reactants will yield the right side. The right side in this case is the CO2 plus H2O. These are called the products. Other parts of the chemical equation, the spaces in front of the compounds, these are going to be referred to as moles. And the thing to remember about moles when balancing chemical equations is that they multiply. They also will multiply in the second semester, but right now they will multiply to balance the chemical equation. The parentheses identifies that compound, that element, its state of matter. G is a gas, S is a solid, L is a liquid. You will use this very rarely. And the last one, AQ, stands for aqueous or aqueous, which is a dissolved salt. The iron 2 or iron 3 lab, those were solutions that were aqueous or aqueous, which means they were dissolved in water. And the last part of our, well, let's do the state of matter here. The state of matter for all these compounds in this chemical equation in your notes, they are all in the gaseous state. And the last thing, the 2 on CO2, that is called a subscript. You cannot change subscripts. You must remain the same. Section at the bottom, counting the atoms. Sometimes when you see water, water will be split into 2 H's and 1 O, but I do prefer this. Water is an H and an OH. There is 1 H and there is 1 OH. The parentheses here, whenever I balance and I split water in this way, H and an OH, whatever I put as far as moles, it affects my H and my OH. That may be explained on the back side when we balance a couple of equations. Number 2, I break this one apart. There are 1 magnesium atom, or there is 1 magnesium atom, and there are 2 chlorine atoms. When balancing chemical equations, I must count them, take inventory is what I call it, to make sure that I have observed the law of conservation of mass. The number 3 has an element, magnesium, and there's 1, but it has a polyatomic. When you see a polyatomic, do remember that it may have parentheses or may not. Keep the polyatomics together. Do not break them apart. It makes balancing of chemical equations much easier. There's 1 magnesium and 2 hydroxides in magnesium hydroxide. Number 4, this one has sorry about that. This one has a mole in front of it of 2. So moles multiply, and it multiplies everything throughout. I have two polyatomics here. I have an NO4, and I have a PO4. So I'm not breaking anything apart. There's three NO4s without the moles, but there's a 2 in front of it, so that would be a total of 6. And there's only one PO4, but I have 2 in front of it, so that would be a total of 2. Keep your polyatomics together, and if you have moles that are in front, we'll multiply them throughout. Number 3, we have lithium and we have oxygen. I will separate the two. There are 6 lithiums because there's 2 in the formula and 3 moles in front, so 3 times 2 is 6. And then there's just 1 oxygen, which 3 times 1 is 3, because moles multiply. Number 6, there's only one polyatomic, the C6H7O2. We break that apart. There are 6 H's, or excuse me, 6 C's, 7 H's, 2 O2's. I'm keeping together the hydroxide OH. There are 3 of them. The 7th one, the copper chromate, this is a polyatomic. CrO4 is a polyatomic, and this one does not require parentheses, so you just through practice, the more times you see it, the more familiar you will be with the polyatomics, that you can group them together even though they do not have a parentheses around them. So there are 2 coppers, and there are 1 chromates. So that's the counting the atoms. We will balance this equation on the front after we do some on the back, because it is a special type of equation. Alright, so on the back side of your paper, we have different types. So we have categories or classifications of different types of equations. They're all chemical equations, but they have a general template. The first one, the H2 plus O2 yields. Eventually, your unit test is similar to this, meaning that you should be able to, the majority of this backside of your notes they're blank, but you should be able to fill this out. State of matter, types of compounds, types of products, and balance of chemical equations would be part of the unit. Now, this first type is the general format, is when I have an element plus an element, and it doesn't have to always be an element plus an element, but if I have this template, I have this type of reaction. If one thing plus another thing yield a new substance, in this case it's a compound, A plus B yields AB. This is called a synthesis equation. Now this one has some special things that we're going to write the equation. If it follows the template, H is A, O is B. If H plus O yield, what do they make? They make, and the only possible things they can make is an O and H together. But in this case, they make the compound water. As I use my formula writing, if oxygen is a -2 and an H is a +1, all right, and they're going to have to equal 0 here. Okay, that how many? I need 2 H's here. I may do the oxidation numbers, I may not do them all the time. Alright, so once I have my equation finished, I have made a compound. This is a synthesis reaction. I'm going to fill in the state of matters. Hydrogen is a gas. Oxygen is a gas. And this leads me to this part right here, is this thing called H-Naphthalchloride. chloride. H Knopf. So H-Naphthalchloride. What that means are these elements here, and it goes in the order of the periodic table: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These elements are what we call diatomic. Crucial to know this. These elements cannot exist by themselves, which means there are always two of them. H is always H2, O is always O2, etc., etc. So if you ever see the word oxygen gas, fluorine gas, when you write your chemical equation, you got to have two of them. If you don't, it's going to be pretty difficult to balance. All right. So we will balance this chemical equation here, this synthesis reaction between hydrogen gas and oxygen gas. Notice that they are diatomic. It makes water. Okay, it does make water. So we will balance them. What I have issue with is the oxygen on the product side. There's not enough of them. I have 2 on the reactant side, but only 1 on the product. So if I have to change something, it's a kind of a back and forth tennis match, that I will do one thing to one side and change it on the other. So I put my moles in front of my water, and that changes my number of hydrogens to now 4. This one I'm not going to split water apart into the HOH. The reason is I don't have HOH on the other side. So sometimes I do, and then sometimes I don't split it apart. But just be aware that it is easy to split apart into the HOH when applicable. Alright, so I fixed the O. I got to come over here and fix the H. It needs 2 moles to get 4 because I changed the product. And then I keep the oxygen the same because I have same number on each side. I'm going to put 1. So it is appropriate to put 1 mole in front of my compounds that, well, I just do that. Anyway, going on. So that's my synthesis reaction. Be aware of the H-Naphthalchlorides, the diatomic elements, when writing our chemical equation. But this is a synthesis. We're making something. All right, the second one you have down there. All right, we'll see H2O on our product side. I only see one thing. When I see one thing, okay, in this case it's a compound. If I have a compound, AB, is going to break down into its component elements, A plus B. What makes up that compound is what it's going to break down into. All right, so this is called a decomposition equation. So water in this case is a liquid. Usually the only time that things are going to be, there's only one liquid right now, and that's water. Okay, so there's nothing in that water but water. So water is going to be broken down into the elements that make it. So using the previous equation above, the synthesis reaction of oxygen gas and hydrogen gas, if we break down water into its component elements, which is hydrogen, it cannot just be H. When water is broken down into its gases that make it, it's broken down to hydrogen gas, and oxygen gas. You have to have the subscript of 2 for the hydrogens and the oxygens. If not, it just doesn't work out. You just got to do it. All right, I got to balance the chemical equation. So, same issue. It's the same equation as I had up above, so it's just backwards. I made water through combustion. I break water down through electrolysis. And I need 2 moles in front of water, 2 moles in front of hydrogen gas, and 1 mole in front of oxygen gas. So it's a back and forth game. I'm doing what I did on the first page as far as I got to count the atoms. If you need to count the atoms, you actually can write them down and keep them organized. Do whatever you need to, okay, to balance those equations. All right, the third equation, these may not be in order. I do apologize for those. This is actually the acid-base neutralization, so let's just do it. All right, so we have an acid-base neutralization. Anything that starts with the letter H is an acid. And we'll just keep it as that for right now. Water is going to be a little tricky, but anything other than water that starts with an H, let's say that, is an acid. If I see the polyatomic OH, the hydroxide, it is a base. Anytime I have an acid plus a base, I'm going to get these products. An acid-base neutralization will always yield water and a salt. So that's the clue. What I'm looking for, why we're doing these types of reactions, is because you're going to have to predict the products, and if you know the template for an equation, you can predict your products much better than not knowing the structure of the 6 types of equations you have on the back side of your notes. So acids, except for the water, start with the letter H. Bases will have OH in them. If I have an alkali or an alkali earth metal, they make basic products. They are bases when dissolved in solution. So these 2 states of matter, let's just fill that in. States of matter for hydrochloric acid is aqueous. It is dissolved in water. Water is not part of the reaction, so we do not use it in the chemical equation. Sodium hydroxide has been dissolved in water. And what we're going to do here is this thing called outside with outside, inside with inside. I match up the first element in the first compound with the outside element, compound, whatever it is, but outside with outside. I'm going to write this down so we have it. And I'm going to match up inside with inside. All right, so matching the outside with outside, I will predict my products. I have an H on my outside matched up with an OH. This is where I like to have HOH as far as water, and when you write water in this way, especially when you have an acid-base neutralization, it makes things a lot easier. Alright, and now I'm going to match up the inside with the inside. Chlorine is the inside element of the first one, and then I have the first element in the second compound. They are matched up. Alright, HOH is water. The negative does not go first. Always the positive is written first. Sodium goes first, then chlorine. Now your knowledge of oxidation numbers again comes into play. Chlorine is a halogen, it's a minus. And sodium is an alkali, it's a plus. I've got to make sure that the oxidation numbers, the sum equals 0. This is a dissolved for the dissolved salt. So we put aqueous. We'll get to that later in solubility. So now I need to balance the chemical equation. If I separate water into HOH, I have hydroxide on both sides of the equations, and I see things much easier. I have one hydrogen, I have one hydrogen. I have one chlorine, I have one chlorine. I have one sodium, I have one sodium. I have one hydroxide, I have one hydroxide. So my balanced chemical equation is 1, 1, 1, 1, because the oxidation numbers of all these are plus minus, so they all neutral out or equal 0. The next one is right above the acid-base neutralization. Acid-base neutralization and double replacement reactions are similar with the outside with outside, inside with inside rule. So this is a double replacement. And the structure is compound AB plus compound CD will yield new compound AC plus new compound BD. All right, so I'm going to predict my products. Outside with outside. K matches up with NO3. So my product, K is a positive, NO3 is a negative. So it is neutral, so that is good. I'm going to put my parentheses. It is aqueous for later reasons we'll find out. I'm going to match inside with inside. Lead matches up with iodine. The positive always goes first. Okay. I have to look at my oxidation numbers on the first. What is the oxidative state of lead here? Well, since nitrate is a minus and there's 2 of them, lead must be a +2. So therefore over here the oxidation number still remains the same, so it is +2. So when I put down iodine, iodine is a halogen, it's minus, I have to write the formula. Now, I is part of the H-Nautical-Bohr rule, but since it's in a compound, I don't have to observe it. I go by the sum of the oxidation numbers must equal 0. This is also, this is not aqueous, this is a solid. Okay, we'll find out why that's a solid later. So I'm going to balance this chemical equation. A double replacement equation, both of the reactants are the aqueous state. Balancing the chemical equation. If I keep my polyatomics together, it makes it a little bit easier. I'm going to keep my KNO3s together. I'm going to do this way just in case. It may be helpful if you do this. The first time I've done this is I get organized. I'm going to write down and record like that. There is 1 potassium. There's 1 iodine. I'm breaking that one apart because I'm going to break it down. There are 1 lead atoms on the reactant side. And I'm going to keep nitrate together. And there are 2 of them. I'm going to separate them by the arrow. Law of conservation of mass says I have to have a K on the product side if I have a K on the reactant side. On the product side, there's 1 potassium. Okay, I'm going to keep them in the same order. There are 2 iodines. There is 1 lead. And there's 1 nitrate. And so this may be a help if you have a hard time balancing chemical equations. I can see what is not balanced. It's the I and the nitrate. I like to balance the nitrates first. Or not the nitrates, but I like to balance the polyatomics. If I balance the polyatomics, then that usually fixes my other. Alright. So I need 2 nitrates on the product side. I put my moles in front of potassium nitrate. When I do that, it changes my total for potassium. It has 2 now, and so does nitrate. So I fixed what I wanted to fix, which was nitrate, but I messed up the K. I still got to fix the I, but check this out. The K and the I are together on the reactant side, so therefore, if I need 2 potassiums, I put a mole of 2 in front of Ki. Therefore, I fix the number of K's to 2, the number of I's to 2, and this is the balanced chemical equation. The other ones do not need anything other than 1 mole, so I will fill that in with the number 1. Next equation here, very similar to the double replacement. These are called single replacement. A single replacement is where there's just one switch. It is the more active, and there's a thing on your backside of the periodic table that has a reference of the activity series. We'll get into that later. One of these metals, it can be a positive ion that switches, or it can be a negative ion that switches. In this case, it's going to be the positive ion because we have 2 metals. All right. Aluminum is a solid, and copper chloride is a solution, an aqueous solution, which means it's dissolved in water. All right. So it's still, I'm going to switch. Aluminum is a +3 because it's by itself. Copper in my formula is a +2 because chlorine is a minus, because I work backwards, and that's why we did that, is because it's super important now to know and identify the oxidation number of the positive by working backwards. If there's 2 chlorines and 1 copper, copper must be in the +2 state. And the oxidation numbers stay the same on the reactant side versus the product side. Very important to remember. So in this case, aluminum is more active than copper, and it will replace copper in solution. Okay, and this is a pretty cool reaction we'll do at some point. So you're going to switch, and the template for a single replacement is element A plus compound BC is going to produce, okay, compound AB plus C. It may not be exact. I messed up on the numbers or the letters there, but I'm switching it. The whole thing is you don't have to use these little templates, the A plus that, if it's confusing. You just look at it. One thing's going to switch. Okay, what's going to switch here? It's the 2 positives. The 2 positives will switch places. So when they switch places, I now have aluminum. Aluminum's +3 joined with chlorine. Chlorine is minus, so therefore there must be 3 chlorines. It is an aqueous solution. What's going to be switched is I'm going to get copper. That's what is by itself. Okay, I make a new compound plus a single element. Copper in this case will be a solid, and I will balance the chemical equation. Alright, so chlorine has a 2 and a 3, so the least common multiple is 6. So to fix and balance that chemical equation, I have 2 on the reactant side, so I need 3, because 3 times 2 is 6. That gives me 3 coppers. So I come over here and fix that. And it gets a back and forth game as far as balancing them. I need to fix the chlorine on the product side. There are 3 of them, so I need 2 moles in front of AlCl3. They give me the 6 that I need. Now I need to fix aluminum on the product side, the reactant side, and there it is. Last, I think it's the last, yep. Last reaction is called a combustion. This is a special reaction, and it's helpful to identify so you know how to attack balancing the chemical equations differently. Combustion equations are going to be, you will notice I have oxygen. Okay? I have oxygen on the reactant side. And when I have something in the presence of oxygen burning, and is what we commonly say, the products are always so I have oxygen, O2 gas will produce water and carbon dioxide. all the time. I don't have to match anything. If I identify if something is burning in the presence of oxygen, my two products are always going to be water and carbon dioxide. The tricky thing with combustion reactions is I'm going to do this. I'm going to balance carbon first. So it's helpful to get organized. This is the same reaction on the first side of your note, so we really don't have to balance that. We can do it here. Just to give you a visual, and you don't have to do this, but it's helpful. Combustion equations are usually the most difficult. On the reactant side, there's 3 carbons, there's 8 hydrogens, and there's 2 O's. On the product side, there's 1 carbon, there's 2 hydrogens, and there's 3 O's. You got it over here. There's 1 oxygen here, and there's 2 oxygens here, so they are in different compounds, but you must add them together to get a total, because we don't care that they're in separate elements or compounds. We care that they're the total oxygen on the product side, so there's 3. Alright, so the first thing I'm going to do is I'm going to fix carbon. I have 3 carbons on the reactant side, and I have 1 on the product, so what do? I need to get the product carbon to 3. How do I do that? Bam. Alright, so 3 times 1 gives me 3 carbons. 3 times 2 is 6, and 6 plus 1 is 7 oxygens. But before we want to fix the oxygens, fix hydrogen. Do that second. Alright, I have 8 hydrogens on the reactant side, and I have 2 on the product side. So how do I fix that? I need to put I need to have 4 moles of water. 4 times 2 is 8. And that fixes the H. And this is why we do oxygen last, because it helps me get this, because we have an odd number. Okay, if we try to fix oxygen when it's odd, it's weird. Okay, there's another trick that we can do here, but you just know that if I have oxygen and I have water and I have carbon dioxide as products, I need to go carbon first, hydrogen second, and then fix O, because that's the last thing. Fix and balance your oxygen. Alright, so when I put 4 moles in front of H2O, that changed my oxygen totals. 4 times 1 is 4, and when I mark it out, it means it's gone away. I'm recounting from 0. 4 times 1, and I'm doing this one right over here. Doing this right here. 4 times 1 is 4, plus the 6 over here, the one that I just highlighted. So 4 plus 6 gives me 10. Now I can fix oxygen a little bit easier because I have 2 on the reactant side. And so what times 2 will give me 10, because moles multiply 5. And there's the state of matter.